Close your eyes now and let yourself drift. Drift beyond the ceiling above you, beyond the sky, and into the infinite embrace of space. We're beginning a journey together, a peaceful voyage through the cosmos. And there's nowhere you need to be, nothing you need to do except simply float and listen. Let's start here, at home, Earth. Our beautiful blue marble suspended in the darkness. From up here, looking down, you can see how our planet is wrapped in the thinnest veil of atmosphere, just 100 kilometers thick. It's so delicate, this blanket of air that makes all life possible. If Earth were the size of an apple, our atmosphere would be thinner than its skin. Imagine that. Everything we've ever known, everyone who has ever lived, protected by something so fragile, so impossibly thin, and yet within this delicate shell, something extraordinary happens. Every single day, our atmosphere catches about 100 tons of dust and sand-sized particles from space. Tiny pieces of asteroids and comets quietly drifting down, becoming part of our world. You're breathing in stardust right now as you rest. Ancient travelers from distant places coming home to settle on your skin, in your lungs. We are, all of us, made of the universe, and the universe keeps sending us reminders. Now let's drift upward, just a little higher. We're leaving Earth's embrace, floating toward our nearest celestial companion, the moon. That gentle light you've gazed at on countless evenings. It's moving away from us, did you know? Very slowly, just 3.8 centimeters every year. About the same rate your fingernails grow. The moon is leaving us inch by inch, century by century. But don't worry. It will stay with us for billions of years yet. There's time. There's always time here in the cosmos. The moon, our faithful companion, is tidally locked to Earth. This means it shows us the same face always. The same craters, the same Maria, those dark patches ancient peoples thought were seas. For all of human history, we've only seen one side of our moon. The far side remained a mystery until 1959, when a Soviet spacecraft finally glimpsed what had been hidden since the moon was born. An entire hemisphere, unseen by human eyes for 4 billion years. Let's pause here. Floating in the space between Earth and Moon. It's so quiet here. No sound can travel in the vacuum of space. There's nothing to carry it. If you could somehow survive here without protection, you could watch the most violent cosmic explosions in complete, perfect silence. The universe, for all its power and fury, is soundless. It's only when its energy reaches an atmosphere, our atmosphere, back home, that it finds a voice. We're going to continue drifting now, moving deeper into our solar system. Past the moon, into the vast dark between worlds. Space isn't empty, though it seems that way. It's filled with radiation, with magnetic fields, with those tiny dust particles making their endless journeys. The distance between Earth and our moon is about 384,400 kilometers. You could fit all the other planets in our solar system side by side in that gap: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, and still have room to spare. The universe is generous with its emptiness, giving everything space to breathe, space to exist. As we drift outward, the sun grows brighter in our view. Our star, feel its warmth even from here. The sun is so large that 1.3 million Earths could fit inside it. Imagine that vastness, and yet, in 8 minutes and 20 seconds, its light crosses 150 million kilometers to reach Earth. The sunlight that warmed your face this morning left the sun just before you poured your coffee. Every sunrise is a message sent 8 minutes earlier, a letter from our star saying, "Here, have another day, have warmth, have light, have life." Rest now in this space between worlds. We've only just begun our journey and already we've traveled so far. There are 91 more wonders waiting for us in the darkness ahead. But for now, just float and breathe and let the gentle immensity of it all wash over you. We'll continue on together into the deeper dark. We're drifting closer to the sun now, but don't worry, we're still far enough away to feel only its gentle warmth, like a distant fireplace on a cold night. Let yourself be drawn toward this ancient light, this heart of our solar system. The sun isn't solid, you know. It has no surface to stand on, no ground beneath your feet. It's a sphere of plasma, superheated gas, swirling and churning in an endless dance. And deep within its core, something miraculous happens. Every second, the sun converts 600 million tons of hydrogen into helium. That's the weight of 1,000 Empire State Buildings transformed from one element into another every single second. This is where the sun's light comes from, not from burning like a fire, but from fusion. The very atoms themselves are joining together, releasing energy, releasing light, releasing the warmth that makes flowers bloom back home. But here's something beautiful to contemplate as you float in this darkness. The light being born in the sun's core right now won't reach the surface for a very, very long time. A photon of light created in the heart of the sun must bounce and scatter through the dense plasma, zigzagging randomly in every direction. It takes that tiny particle of light somewhere between 100,000 and 200,000 years to finally break free and stream into space. The sunlight you saw today began its journey before humans learned to speak, before we painted on cave walls, before we even knew we were human. Ancient light touching your face. Let's drift past the sun now, letting it fall behind us and venture toward the inner planets. Here comes Mercury, the closest world to our star. Swift Mercury racing around the sun. It completes an entire orbit in just 88 Earth days. But here's the strange part. Mercury rotates so slowly on its axis that one day on Mercury, from sunrise to sunrise, lasts 176 Earth days. That's 2 Mercury years in a single Mercury day. Imagine that, experiencing 2 complete trips around the sun between one sunrise and the next. Time moves differently depending on where you stand in the cosmos. We're passing Mercury now, moving outward, and here comes Venus. Beautiful Venus, the morning star, the evening star, draped in thick clouds that glow golden in the sunlight. Venus is almost Earth's twin in size, but oh, how different she is. Those clouds aren't water vapor, they're sulfuric acid, and they trap heat so efficiently that Venus is the hottest planet in our solar system, even hotter than Mercury. The surface temperature on Venus reaches about 465 degrees Celsius, hot enough to melt lead. But perhaps the strangest thing about Venus is this: she spins backward. While almost every other planet rotates counterclockwise when viewed from above, Venus turns clockwise, slowly, lazily. One Venus day lasts 243 Earth days, longer than a Venus year. She takes her time with everything, Venus. She's in no hurry at all. Drifting onward now past our own Earth, there she is, that blue jewel we left behind, looking so peaceful from here. And we arrive at Mars, the red planet. The color comes from rust, from iron oxide in the Martian soil. Mars is a desert world, cold and dry now, but once, billions of years ago, Mars had rivers. It had lakes, perhaps even an ocean. Water flowed across its surface under a thicker atmosphere. You could have heard wind whistling through Martian canyons, seen clouds drifting across a different sky. But Mars is smaller than Earth, and its lower gravity couldn't hold on to that atmosphere. It escaped into space gradually, and the water disappeared, frozen at the poles or locked beneath the surface. Mars is a memory of what was, a reminder that planets, like everything else, change. And speaking of Martian landscapes, Mars is home to Olympus Mons, the largest volcano in our entire solar system. It rises 21 kilometers above the surrounding plains, nearly 2.5 times the height of Mount Everest. If you could stand at its base and look up, the summit would be beyond the horizon, hidden by the curve of the planet itself. And yet, its slopes are so gentle that you could walk up them without even realizing you were climbing a mountain. The volcano is so vast that it bends with the curve of the world. Let's rest here a moment, floating in the space between Mars and what comes next. We're approaching a boundary now, a threshold in our solar system. Beyond Mars lies the asteroid belt, a ring of ancient rubble orbiting the Sun, leftover pieces from when the planets were forming 4.6 billion years ago, thousands upon thousands of rocky fragments tumbling through the darkness. But despite what you might have seen in movies, the asteroid belt isn't crowded at all. If you were standing on one asteroid, you likely wouldn't even be able to see another with your naked eye. Space has room for everything, always. Beyond the asteroid belt, something changes. We're leaving the realm of the small, rocky worlds behind. Ahead lies the domain of giants, vast spheres of gas and liquid, worlds so large they dwarf everything we've seen so far. And the first of these giants is coming into view now, growing larger with every moment. There. Do you see it? That swirling, banded sphere, with its great red eyes staring out into the dark. Jupiter is waiting for us. Rest now as we drift closer. Breathe slowly. Let the darkness hold you. We have so much more to see, you and I, but there's no rush. The universe has been here for billions of years, and it will wait for us. It will always wait. We'll continue on together into wonder. Jupiter, the king of planets. As we approach, you can see why the ancients named it after their mightiest god. This world is enormous, so large that all the other planets in our solar system could fit inside it with room to spare. More than 1,300 Earths could nestle within Jupiter's vast embrace. And yet, despite this tremendous size, Jupiter spins faster than any other planet. A day on Jupiter lasts just under 10 hours. Imagine a world 11 times wider than Earth, whirling through space like a cosmic ballet dancer, completing a full rotation before you've even finished your morning routine. As we draw closer, you can see the bands, those beautiful stripes of cream and orange and brown, swirling across Jupiter's face. These are storms, currents in Jupiter's atmosphere, jet streams of gas flowing at hundreds of kilometers per hour. Jupiter has no solid surface to slow these winds, no mountains or oceans to break their flow. The storms just continue century after century, some of them larger than entire planets. And there, do you see it? That great red oval, that eye staring out into space. The great red spot. It's a storm, an anticyclonic tempest that has been raging for at least 400 years, probably much longer. When Galileo first turned his telescope toward Jupiter in 1610, this storm may have already been ancient. It's so large that 2 or 3 Earths could fit inside it side by side. Imagine a hurricane that has lasted for centuries, churning in that poisonous atmosphere, never weakening, never finding rest. And yet from here, floating in the silence of space, it looks almost peaceful, beautiful even. Look around Jupiter now and you'll see them, tiny points of light circling their giant parent. Moons. Jupiter has at least 95 known moons, and there may be more we haven't discovered yet, small irregular fragments captured by Jupiter's immense gravity. But 4 of them are special, large enough to be worlds in their own right. Galileo saw them through his primitive telescope 4 centuries ago, 4 wandering stars that changed our understanding of the cosmos. We call them the Galilean moons, Io, Europa, Ganymede, and Callisto. Let's drift toward them now, toward Europa. This moon is wrapped in ice, a frozen shell covering the entire world. But beneath that ice, something extraordinary waits. Europa has a global ocean, liquid water beneath the frozen surface, kept warm by the tidal forces of Jupiter's gravity flexing and squeezing the moon's interior. That ocean is deep, perhaps 100 kilometers deep, containing twice as much water as all of Earth's oceans combined. Imagine that, a vast dark sea, hidden beneath the ice, never seeing sunlight, never knowing a star's direct warmth. Could something live in those dark waters? We don't know yet. But the ocean is there, sloshing gently beneath the ice as Europa orbits Jupiter, a secret sea waiting to be explored. Move your attention now to Ganymede, the largest moon in our entire solar system. Ganymede is bigger than the planet Mercury, a world of ice and rock with its own magnetic field, the only moon known to have one. If Ganymede orbited the Sun directly instead of Jupiter, we would call it a planet without hesitation. But here it is, a giant world forever bound to an even greater one, dancing the same eternal dance. We're drifting away from Jupiter now, letting it fall behind us, its moons slowly shrinking to points of light. As we travel outward, deeper into the solar system, the sunlight grows dimmer, the distances grow vaster. Space stretches out before us, empty and patient. This is the quiet part of the solar system, the cold reaches where ice becomes more common than rock, where a year is measured not in months, but in decades. And there, emerging from the darkness like a jewel, is Saturn. Oh, Saturn! Even from this distance you can see them, those magnificent rings tilted at an angle, catching the pale sunlight. Of all the wonders in our solar system, perhaps nothing is more elegant, more impossibly beautiful than Saturn's rings. They look solid from here, don't they? Like a disk of material, a platform you could walk across. But they're not solid at all. Those rings are made of countless individual pieces, chunks of water ice, some as small as grains of sand, others as large as houses or mountains. Billions upon billions of fragments, each one orbiting Saturn independently, all held in place by gravity and subtle resonances with Saturn's moons. And here's something that might surprise you. Those vast, magnificent rings are remarkably thin. If you could see them edge on, they would almost disappear. The rings span more than 280,000 kilometers from edge to edge, almost 3/4 of the distance from Earth to the Moon, and yet they're typically only about 10 meters thick. Imagine a disk of paper as wide as 2 football fields laid end to end. That's roughly the same proportion. The rings of Saturn are, in their own way, as delicate as they are grand. Let's drift closer now, passing through the ring plane. Don't worry, there's plenty of space between the particles, and approaching Saturn itself. Like Jupiter, Saturn is a gas giant with no solid surface, but Saturn is special. It's the least dense planet in our solar system. In fact, if you could find an ocean large enough, Saturn would float in it. Imagine that, a planet the size of 764 Earths, light enough to rest on water, like a cosmic bath toy bobbing in an impossible sea. As we circle Saturn, look at all those moons. Saturn has at least 146 known moons, more than any other planet. Some are tiny, irregular fragments barely a kilometer across. Others are substantial worlds. There's Titan, visible even from here, Saturn's largest moon, shrouded in a thick orange haze. Titan is the only moon in our solar system with a substantial atmosphere, thicker even than Earth's. Beneath those orange clouds are lakes and rivers, but not of water. They're liquid, methane and ethane, hydrocarbons flowing across an alien landscape at temperatures far below freezing. It rains on Titan, but the rain is methane, falling slowly in the thick atmosphere, pooling in lakes near the poles. A world with weather, with seasons, with a hydrological cycle, but made of entirely different substances than the world we call home. Rest here for a moment, floating above Saturn's clouds, watching the rings cast their shadows on the planet's surface. Feel how far you've traveled. The sun is so distant now, so small compared to how it looks from Earth. Out here, in the cold and the quiet, you can truly feel the scale of things, the vast distances between worlds. But you're not alone. You're here, conscious, aware, a thinking being contemplating the cosmos. And that's perhaps the most remarkable thing of all. We'll continue outward soon, into even colder, even more distant realms. But for now, just breathe and marvel, and let the wonder of it all wash through you. The universe is patient. It will wait for us to continue. We're leaving Saturn now, drifting away from those glorious rings, watching them narrow to a thin line, then to a point of light, then finally disappearing into the darkness behind us. The sun is small now, just another bright star in the sky, though still brighter than all the rest. Out here, its warmth is barely a whisper. We're entering the outer solar system, where worlds take not years but decades to complete a single orbit, where the cold is so profound that the very air would freeze solid. Ahead of us, pale and blue-green, floats Uranus. Strange, distant Uranus. Even the way we say its name has changed over the years. Astronomers now prefer Uranus to avoid the jokes, the snickers. But this world deserves our respect, not our laughter. Uranus is peculiar, unique among all the planets for one remarkable reason: it rotates on its side. While other planets spin more or less upright as they orbit the Sun, Uranus rolls along like a barrel, its axis tilted 98 degrees from vertical. Imagine if Earth did this. The North Pole would point directly at the Sun for half the year, then directly away for the other half. On Uranus, each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. A single season lasts for decades. If you were born during Uranian summer, you'd be middle-aged before winter arrived. What caused this strange tilt? We believe that long ago, billions of years in the past, something massive collided with Uranus, perhaps an Earth-sized object, striking with such force that it knocked the entire planet onto its side. Uranus has been rolling through space ever since, a permanent reminder of that ancient, violent encounter. The universe is not always gentle, even in its beauty. As we drift closer, you can see that Uranus has rings too, though nothing like Saturn's magnificent hoops. Uranus has 13 known rings, thin and dark, made of material so black they barely reflect any light at all. They're almost invisible, discovered only in 1977, when astronomers noticed starlight blinking on and off as the rings passed in front of a distant star. These rings are young, cosmically speaking, perhaps only 600 million years old, formed from the shattered remains of moons that ventured too close and were torn apart by Uranus's gravity. Let's continue outward now into the deepest cold, the farthest reaches of our planetary system. The journey from Uranus to Neptune takes us across nearly 1.5 billion kilometers of empty space. Out here, messages traveling at the speed of light take hours to cross from one world to another. If you tried to have a conversation with someone on Neptune from Earth, you'd send your question, wait over 4 hours for it to arrive, then wait another 4 hours for their response to return. The distance imposes a profound silence, a cosmic delay that makes real-time communication impossible. And there, finally, Neptune. The last of the giant planets, the farthest world of substantial size in our solar system. Neptune is a deep, rich blue, colored by methane in its atmosphere, absorbing red light. It's slightly smaller than Uranus, but more massive, denser, and far more active. Despite being the coldest planet in our solar system, with temperatures dropping to -214 degrees Celsius, Neptune has the fastest winds ever recorded on any planet. These supersonic gales rage at speeds up to 2,100 kilometers per hour, nearly twice the speed of sound. Imagine standing in wind, moving at 2,100 kilometers per hour. You couldn't, of course, it would be instantly fatal, but the thought alone is staggering. These aren't breezes, they're screaming rivers of frozen gas, tearing around the planet faster than any hurricane Earth has ever known. Neptune takes 165 Earth years to complete a single orbit around the Sun. Since its discovery in 1846, Neptune has only just completed its first full orbit as observed by human eyes. In 2011, Neptune returned to the same position in the sky where it was first spotted. Anyone born when Neptune was discovered would need to live to 165 years old to see it complete one full year. The universe measures time differently than we do, in rhythms vast and slow. Look there, near Neptune, that small, irregular shape, that cratered world. That's Triton, Neptune's largest moon, and one of the strangest objects in our solar system. Triton orbits Neptune backward in the opposite direction to Neptune's rotation. This tells us something important. Triton wasn't born here. It was captured, pulled from somewhere else by Neptune's gravity, perhaps from the Kuiper Belt beyond. Triton is a prisoner, slowly spiraling inward. Millions of years from now, it will drift too close to Neptune and be torn apart by tidal forces, its remains forming a new ring system around the planet. But that's far in the future. For now, Triton endures, and despite the incredible cold, Triton's surface temperature is -235 degrees Celsius, making it one of the coldest objects in the solar system. This moon is geologically active. Triton has geysers, fountains of nitrogen gas erupting from beneath its frozen surface, shooting ice particles up to 8 kilometers into the thin atmosphere before falling back down like snow. Even here, in the frozen edge of the solar system, worlds remain alive, changing, active. The universe never truly rests. We're beyond the planets now, drifting into the realm of ice and darkness. Ahead lies the Kuiper Belt, a vast ring of frozen bodies orbiting the Sun beyond Neptune, countless small worlds, fragments left over from the solar system's formation, and somewhere among them, tumbling through the darkness, is a world that once bore the name planet, Pluto. Small, distant Pluto, demoted to dwarf planet status in 2006, but no less real, no less worthy of wonder for the change in classification. Pluto is tiny, smaller than Earth's moon, and its orbit is strange, elongated and tilted compared to the planets. But when the New Horizons spacecraft flew past Pluto in 2015, we saw something unexpected, a heart, a vast, bright, heart-shaped region on Pluto's surface made of nitrogen ice. Tombor Regio, they named it, after Pluto's discoverer. And within that heart, nitrogen glaciers flow, mountains of water ice rise up to 3,500 meters high, and a thin atmosphere barely clings to the surface, freezing and sublimating with the seasons. Pluto, it turns out, is not dead, not inactive. Even here, nearly 6 billion kilometers from the Sun, geological processes continue. Mountains form, ice flows, atmospheres come and go. The universe is alive in ways we're only beginning to understand. Rest here now at the edge of the planetary realm. Behind us, the Sun is just a bright star, indistinguishable from many others, save for its slightly greater brilliance. The planets are invisible from here, lost in the darkness, specks of dust scattered across an impossible distance. Ahead lies... what? More darkness, certainly. But also stars, so many stars, more stars than you could count in 1,000 lifetimes. We're about to leave our solar system behind and voyage into interstellar space. But first, rest. Breathe slowly. Feel the silence, the vastness, the profound peace of the deep dark between worlds. You've traveled so far already, you've seen wonders most of humanity will only ever imagine. The journey continues, the stars are waiting. And we're going to meet them. We're crossing a threshold now, an invisible boundary in space. Behind us, the sun's influence still reaches out. Its gravity, its solar wind, the stream of particles flowing outward from its surface. But ahead lies something different. We're approaching the heliopause, the edge of our sun's domain, where the solar wind finally weakens and mingles with the interstellar medium, the thin gas that fills the space between stars. Only 5 human-made objects have ever crossed this boundary. Voyager 1, launched in 1977, became the first in 2012, followed by Voyager 2 in 2018. These twin spacecraft, no larger than a small car, have traveled farther from home than anything humanity has ever built. Voyager 1 is now more than 24 billion kilometers from Earth, and yet it still sends us messages. Faint whispers of radio waves taking over 22 hours to reach us, traveling at the speed of light. When we receive a signal from Voyager 1, we're hearing news from a day ago, a message sent from the edge of everything we've ever known. Let's pause here, floating at this cosmic shoreline, and look back, turn around, and look toward the sun. From this distance, our star is just a point of light, unremarkable among the darkness. And Earth? Earth is invisible, completely invisible. No telescope we possess could pick it out from here. It's lost in the sun's glare, a speck far too small and faint to see. In 1990, Voyager 1 turned its camera back toward home and took a photograph from 6 billion kilometers away. Earth appeared as less than a single pixel, a pale blue dot suspended in a sunbeam. That's all we are from out here. Everything you've ever known, everyone you've ever loved, every human achievement and failure, every war and peace, every joy and sorrow, all contained in that single point of light, now invisible in the darkness behind us. But we're not finished with the sun's realm yet. Even here, even at this tremendous distance, the sun's gravity still holds sway. Far beyond the planets, far beyond Pluto and the Kuiper Belt, lies the Oort cloud, a vast spherical shell of icy bodies surrounding our solar system. This cloud is so distant, so enormous, that it defies easy comprehension. It begins perhaps 1,000 times farther from the sun than Earth is, and extends outward nearly halfway to the nearest star. The Oort cloud may contain trillions of comets, frozen chunks of ice and rock, sleeping in the darkness, taking millions of years to complete a single orbit. Occasionally, something disturbs one of these distant travelers, a passing star perhaps, or the subtle tug of the galaxy's gravity, and it begins a long fall toward the inner solar system, where it will become a comet, a spectacular visitor gracing our skies before returning to the dark. The Oort cloud is so vast that an object at its outer edge would take somewhere between 2 million to 6 million years to complete one orbit of the sun. Imagine that. Civilizations could rise and fall, species could evolve and go extinct, ice ages could come and go, all in the time it takes one of these distant objects to make a single journey around our star. We've never actually seen the Oort cloud, it's too far away, its object's too small and dark, but we know it must be there because comets keep arriving, falling inward from the deep cold, their orbits telling the story of their distant origin. We're going to leave the Oort cloud now, leave the sun's gravitational embrace entirely, and venture into true interstellar space. The space between stars, this is the void, the great emptiness, though even here it's not truly empty. Interstellar space contains about 1 atom per cubic centimeter, a density so low it makes the best vacuum we can create on Earth seem crowded by comparison. 1 atom per cubic centimeter. In every handful of space, just a few dozen atoms, mostly hydrogen, drifting alone in the darkness. But look ahead now. Do you see that light? That's Alpha Centauri, the nearest star system to our Sun. Actually, it's not 1 star, but 2 stars orbiting each other closely, and a smaller, dimmer third companion, Proxima Centauri, orbiting the pair at a great distance. Proxima Centauri is the closest of the 3, the nearest star to our solar system, and yet it lies 4.24 light-years away. That means the light you see from Proxima Centauri left that star over 4 years ago. You're seeing the past. If Proxima Centauri exploded right now, we wouldn't know for more than 4 years. The universe imposes a speed limit, the speed of light, 300,000 kilometers per second, and even that incredible speed becomes frustratingly slow across interstellar distances. If we wanted to reach Proxima Centauri using our fastest current spacecraft, it would take over 70,000 years. 70,000 years. The entire span of recorded human history is less than 1/10 of that journey. And Proxima Centauri is our closest neighbor. The next nearest star system is more than twice as far away. The stars, for all their brilliance, are extraordinarily isolated from one another. The universe keeps them apart, separated by gulfs of space so vast that light itself labors to cross them. And yet Proxima Centauri has a planet. Proxima Centauri b, a world slightly larger than Earth, orbiting in what might be the habitable zone, where temperatures could allow liquid water to exist. We discovered it in 2016 using incredibly subtle measurements of how the planet's gravity tugs on its parent star. We've never seen Proxima Centauri b directly, it's far too faint, but we know it's there. A world orbiting the nearest star. Could there be oceans on that world? Continents? Weather? Could something live there, something looking up at its own night sky, seeing our sun as just another star, wondering if anything exists on the worlds that might orbit it? We don't know. We may never know, but the possibility alone is extraordinary. As we drift through the void between our Sun and Proxima Centauri, surrounded by darkness, take a moment to feel this. The profound silence, the incomprehensible distance, the patience the universe requires of anyone who would cross from one star to another. Space is not hostile. Hostility implies intent. Space is simply indifferent, vast beyond measure, and governed by laws that care nothing for our wishes or our timescales. And yet, despite all this, despite the cold and the emptiness and the impossible distances, here you are, conscious, aware, a pattern of atoms that learned to think, to wonder, to imagine journeys across the cosmos. You are made of star stuff, Carl Sagan once said, and he was right. The atoms in your body were forged in the hearts of ancient stars, scattered across space when those stars died, gathered together by gravity into new worlds, new possibilities. You are the universe experiencing itself. And right now, in this moment, the universe is traveling from one star to another, marveling at the journey. Rest now. Breathe. We're halfway across the void, with trillions more stars ahead of us, countless more wonders waiting in the darkness. The journey continues, always continues, and we have all the time in the universe. We're approaching Proxima Centauri now, though approaching is a generous word for drifting across 4 light-years of emptiness. As we draw closer, you can see that this star is nothing like our Sun. Proxima Centauri is a red dwarf, small and dim, glowing with a deep crimson light. It's only about 1/8 the mass of our Sun, and it produces just 0.17% of the Sun's luminosity. If you replaced our Sun with Proxima Centauri, Earth would be plunged into a cold, dim twilight, barely brighter than a moonlit night. And yet, red dwarfs like Proxima Centauri are the most common type of star in our galaxy. About 70% of all stars are red dwarfs, small, cool, and incredibly long-lived. Because red dwarfs burn their fuel so slowly they can live for trillions of years. Our Sun will die in about 5 billion years, swelling into a red giant before shedding its outer layers. But Proxima Centauri? Proxima Centauri will still be shining long after our Sun is gone, long after every star like our Sun has burned out and faded away. In the far future of the universe, when most of the stellar fireworks have ended, red dwarfs will be the last lights still burning, solitary candles in an increasingly dark cosmos. They are the patient ones, the enduring ones, content to glow gently for timescales that make the current age of the universe seem like a fleeting moment. Let's move onward now, leaving Proxima Centauri behind, venturing deeper into our stellar neighborhood. The stars are still sparse here. Even in our local area, the distances are immense. But ahead, perhaps 8.6 light-years from our Sun, shines Sirius, the brightest star in Earth's night sky. Sirius is actually 2 stars, Sirius A, a brilliant blue-white star twice as massive as our Sun, and Sirius B, a tiny, incredibly dense companion. Sirius B is a white dwarf, the collapsed core of a star that exhausted its fuel millions of years ago. It's about the size of Earth, but it contains roughly the mass of our Sun. Imagine that, an entire star's worth of matter compressed into a sphere the size of our planet. A teaspoon of material from Sirius B would weigh about 5 tons. The gravity at its surface is so intense that if you could somehow stand there, which you couldn't, you would weigh about 350,000 times more than you do on Earth. The atoms themselves are crushed together, their electron clouds stripped away, packed so tightly that the star can barely be called matter. In any sense we normally understand, it's something else, degenerate matter held up not by atomic structure but by quantum mechanical pressure. Sirius B is a ghost, the remains of a once mighty star, now cooling slowly in the darkness, taking billions of years to fade away completely. We're traveling faster now, leaping across light years, and the stars are becoming more numerous around us. We're moving toward the heart of our galaxy, toward the great spiral of the Milky Way. Look around. Do you see how the stars are arranged? We're not randomly scattered through space. We're part of something larger, something beautiful. The Milky Way is a barred spiral galaxy with elegant arms of stars, gas and dust spiraling outward from a central bar-shaped structure. Our Sun sits about 26,000 light-years from the galaxy's center, nestled in a minor arm called the Orion Spur, between 2 larger spiral arms. The Milky Way is vast. It contains somewhere between 100 billion and 400 billion stars. We can't count them precisely because dust and gas block our view of much of the galaxy. But think about that number for a moment. Hundreds of billions of stars, each one potentially surrounded by planets, each planet a unique world with its own geology, its own history. If only a tiny fraction of those planets are like Earth, there could still be millions of worlds where life has taken hold, where something is growing, evolving, perhaps even wondering if it's alone in the universe. The Milky Way is also spinning. Everything in it, the stars, the gas clouds, our Sun, our solar system, all of it is rotating around the galactic center. Our Sun travels at about 828,000 kilometers per hour, on this cosmic journey. And yet, even at that tremendous speed, it takes approximately 225 million years to complete one orbit around the galaxy. We call this a galactic year. The last time our Sun was in this position in the galaxy, dinosaurs were beginning their reign on Earth. Since Earth formed 4.5 billion years ago, our world has completed only about 20 orbits around the galactic center, 20 galactic years, and that's how long Earth has existed. As we travel inward toward the galaxy's center, the stars grow denser around us. Here, in the bulge of the galaxy, stars are packed more tightly together. If Earth orbited a star here, the night sky would be spectacular. Dozens of stars bright enough to cast shadows, the heavens ablaze with light. There would be no true darkness, no true night, just an eternal twilight glowing with the combined light of countless nearby suns. But we're moving deeper still, toward the very heart of the galaxy. And at the center, at the absolute center of the Milky Way, hidden behind vast clouds of dust and gas, lies something extraordinary, something powerful, something that shouldn't exist and yet does, a supermassive black hole. It has a name, Sagittarius A star, pronounced Sagittarius A star. We can't see it directly, black holes emit no light, but we can see its effects. Stars near the galactic center orbit something invisible, moving at tremendous speeds, their paths bent by immense gravity. By tracking these stars, we've determined that Sagittarius A star has a mass of about 4 million times that of our Sun, all compressed into a region smaller than the orbit of Mercury. In 2022, astronomers captured the first image of Sagittarius A star, not the black hole itself, but the glowing ring of superheated matter spiraling around it, light bent and twisted by gravity so intense it warps the very fabric of space and time. Black holes are places where gravity has won completely, where matter has collapsed so thoroughly that not even light can escape. At the center of a black hole lies the singularity, a point where density becomes infinite and our understanding of physics breaks down entirely. We don't know what happens there. General relativity predicts the singularity but cannot describe it. It's a place where the equations that govern the universe simply stop working. A mystery wrapped in an event horizon, the boundary beyond which nothing, not even information, can return. And yet, despite their destructive power, black holes are also creators. As matter spirals into a black hole, it heats up, radiating enormous amounts of energy. These accretion disks can outshine entire galaxies. And the jets that some black holes produce, twin beams of particles accelerated to nearly the speed of light and shot outward along the black hole's rotational axis, these jets can stretch for millions of light years, influencing star formation across vast regions of space, destruction and creation forever intertwined. The universe wastes nothing. Let's not venture too close to Sagittarius A star. Instead, let's turn outward again, rising above the galactic plane. From here, from above, you can see the Milky Way in all its glory, a great spiral of light, 100,000 light-years across, rotating slowly in the darkness. 200 billion stars or more, countless worlds, endless stories written in light and gravity and time. This is our island universe, our home galaxy. And it is just one. Look beyond the Milky Way now. Look at the darkness between the spiral arms. Do you see those faint smudges of light? Those aren't stars. Those are other galaxies. Rest now as we prepare to leave the Milky Way behind. Feel the weight of what you've seen, the distances, the timescales, the sheer abundance of creation. Stars beyond counting, worlds beyond imagining, and all of it bound together by gravity's gentle hand, spinning through the darkness, turning, always turning. We're going to go farther now, farther than you can easily imagine. We're going to visit other galaxies, other structures, the large-scale architecture of the universe itself. But first, breathe, rest. Let the wonder settle into your bones. The cosmos is patient, the cosmos is vast, and the cosmos is waiting to show you more. We're rising now, climbing above the Milky Way's spiral arms, watching our galaxy shrink below us. As we pull away, the individual stars blur together into rivers of light, and the grand structure becomes clear, those graceful spiral arms, the bright central bulge, and surrounding it all, something invisible but vast. The Milky Way is wrapped in a halo of dark matter, an enormous sphere of mysterious substance that we cannot see, cannot touch, but know must be there. Dark matter makes up about 85% of all matter in the universe. It doesn't emit light, doesn't absorb light, doesn't interact with normal matter, except through gravity. And yet there's 5 times more of it than the familiar matter that makes up stars and planets, and you and me. The universe, it turns out, is mostly made of something we don't understand. As we drift farther from the Milky Way, other galaxies begin to appear around us like fireflies emerging at dusk. There, that beautiful spiral, that's Andromeda, the nearest large galaxy to our own. Andromeda is slightly larger than the Milky Way, containing perhaps 1 trillion stars, and it lies 2.5 million light-years away. The light you see from Andromeda left that galaxy 2.5 million years ago, when our ancestors were just beginning to walk upright on the African savanna. You're looking back in time, seeing Andromeda not as it is now, but as it was in the deep past. And here's something beautiful and inevitable. Andromeda and the Milky Way are moving toward each other. Gravity is pulling our galaxies together, and in about 4.5 billion years, they will collide. Don't worry, galactic collisions aren't like car crashes. The stars are so far apart that they'll mostly slide past each other like 2 clouds of fireflies interpenetrating. But the galaxy's shapes will be disrupted, their spiral arms torn apart and reformed. Over hundreds of millions of years, the 2 galaxies will merge, creating a single, enormous, elliptical galaxy. Astronomers have already given this future galaxy a name, Milkomeda. It's our destiny, written in gravity's patient script. Look around us now. The Milky Way and Andromeda aren't alone. We're part of something called the Local Group, a collection of more than 80 galaxies bound together by gravity. Most of them are small dwarf galaxies, faint collections of a few billion stars orbiting the larger galaxies like moons around planets. The Local Group spans about 10 million light-years across, a vast region, and yet just a tiny neighborhood in the much larger cosmos. Beyond the Local Group, you can see other galaxy groups, other clusters, scattered through the darkness. And the farther you look, the more galaxies appear, until they fill the visible universe like sand on a beach. Current estimates suggest there are about 2 trillion galaxies in the observable universe. 2 trillion, each one containing millions, billions, or even trillions of stars. The numbers become so large they lose meaning, become just sounds, just syllables, and yet each of those galaxies is real, a vast island of stars and worlds as real as the Milky Way, each with its own history, its own story, written in light. We're going to travel toward one of the densest concentrations of galaxies nearby, the Virgo cluster. As we approach, you can see them multiplying around us, galaxies by the hundreds, even thousands, all bound together by gravity. The Virgo cluster lies about 65 million light-years from us and contains over 1,300 galaxies. Some are spirals like the Milky Way, their arms elegantly curved. Others are ellipticals, smooth and featureless, shaped like footballs or spheres. Still others are irregular, chaotic tangles of stars with no clear structure at all. At the heart of the Virgo cluster sits M87, a giant elliptical galaxy containing several trillion stars. M87 is extraordinary not just for its size, but for what lies at its center. Like the Milky Way, M87 has a supermassive black hole at its core, but this one is far more massive than Sagittarius A star. The black hole at the center of M87 has a mass of about 6.5 billion times that of our Sun. In April 2019, this became the first black hole ever directly imaged by humanity. The Event Horizon Telescope, not a single telescope, but a network of radio dishes scattered across the entire Earth, working together, captured that iconic image, a bright ring of light with a dark shadow at its center. The shadow isn't the black hole itself, but the region where light has been so severely bent by gravity that it's been pulled into the event horizon, lost forever. That image showed us the face of a black hole, a photograph of the unseeable. M87's black hole is also producing a jet, a narrow beam of particles and energy shooting outward from near the event horizon at almost the speed of light. This jet extends for at least 5,000 light-years, punching through the galaxy and out into intergalactic space. The energy required to sustain such a jet is difficult to comprehend, more energy than millions of stars produce, all focused into a narrow beam. Black holes, we're learning, aren't just cosmic vacuum cleaners, they're engines powering some of the most energetic phenomena in the universe. Let's rise higher now, pulling back to see even larger structures. As we zoom out, the galaxies begin to form patterns. They're not scattered randomly through space, they're organized into a vast cosmic web. Galaxies gather along filaments, long strands of matter, stretching across hundreds of millions of light-years. Between these filaments lie vast voids, enormous regions containing very few galaxies at all. The universe at the largest scales looks like foam or a spider's web, dense in some places, empty in others, structured by the invisible hand of dark matter and shaped by billions of years of gravity's patient work. One of the largest structures we know of is the Sloan Great Wall, a cosmic filament of galaxies stretching across 1.37 billion light-years. Light takes 1.37 billion years to travel from one end to the other. When light left one side of the Sloan Great Wall, Earth was inhabited only by single-celled organisms. By the time that light reaches the other side, everything we call complex life, every plant, every animal, every moment of human history, will have unfolded in the time it took light to make the journey. The universe builds cathedrals from galaxies, structures so vast that light itself becomes slow in comparison. As we float here, suspended among galaxy clusters and filaments, take a moment to absorb what you're seeing. This is the universe at its largest scale, billions of galaxies, trillions of stars, numbers that dwarf comprehension. And yet it's all bound together, all interconnected. Gravity links every galaxy to every other, however faintly. The light from distant galaxies has traveled for eons to reach your eyes. In a very real sense, the entire universe is touching you, reaching across space and time to deliver photons that end their ancient journeys in your retina. You are not separate from this vastness. You are part of it. The atoms in your body were forged in stars, scattered by supernovae, gathered by gravity, shaped by chemistry and biology into the pattern that is you. Every breath you take contains atoms that were once inside stars, that drifted through space for billions of years before arriving here, before becoming part of this moment, this consciousness, this sense of wonder as you contemplate the cosmos from which you came. Rest now in the gentle spaces between galaxies. We're going to venture even farther soon to the very edge of the observable universe, to the beginning of time itself. But for now, simply float and marvel, and know that you are home. Wherever you are in the universe, you are always home, because you are made of the universe itself. The stars are patient. The cosmos is kind. And we will continue together into the deepest mysteries, the most ancient light. We're traveling outward now faster than light itself could travel, because this is imagination, and imagination knows no speed limits. We're leaving the local cosmic web behind, zooming past galaxy clusters and superclusters, watching the universe's grand architecture blur into a sea of light. As we pull back farther and farther, something remarkable happens. The clumpiness begins to smooth out, the filaments and voids start to blend together, and the universe begins to look uniform, homogeneous. At the very largest scales, every region of space looks statistically similar to every other region. This is one of the great surprises of cosmology. The universe, despite all its local complexity, is remarkably uniform when viewed as a whole. We're approaching the edge now, not an edge in space. The universe may well be infinite, but an edge in time. Light takes time to travel, and the farther we look outward, the farther back in time we're seeing. There's a limit to how far we can see, not because space ends, but because the universe itself had a beginning. Beyond a certain distance, we're looking back to a time before stars existed, before galaxies formed, to an era when the universe was young and very different from what it is today. The observable universe, the sphere of space from which light has had time to reach us, spans about 93 billion light-years in diameter. Wait, you might think, if the universe is only 13.8 billion years old, how can we see things 46.5 billion light-years away? It's because the universe itself has been expanding. While light has been traveling toward us, space has been stretching, carrying distant objects farther away, so we can see light from regions that are now much farther than 13.8 billion light-years distant. The universe is playing a cosmic trick, expanding the very stage upon which the light performs its ancient journey. And the expansion is accelerating. In 1998, astronomers discovered something that shook cosmology to its core. Distant supernovae were dimmer than expected, which meant they were farther away than they should be. The universe isn't just expanding, it's expanding faster and faster. Something is pushing space apart, something we call dark energy. We don't know what dark energy is, we just know it's there, accounting for about 68% of all the energy in the universe. Dark matter makes up about 27%. Normal matter, the stuff we can see, the atoms that make up stars and planets and us, makes up only about 5% of the universe. We are made of the rarest substance in existence. Everything we've ever seen or touched or measured is just the foam on the cosmic ocean, floating atop vast, invisible depths we barely understand. As we look deeper into space and time, the galaxies change. The ones in the far distance appear younger, smaller, less structured. We're seeing them as they were billions of years ago, when they were still forming, still gathering matter, still lighting their first stars. And beyond the most distant galaxies, there's something else, a glow, a faint, uniform light coming from every direction at once, pervading all of space. This is the cosmic microwave background radiation, the oldest light in the universe. It was emitted 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form for the first time. Before this moment, the universe was so hot and dense that electrons and protons couldn't combine. They were constantly being torn apart by energetic photons. The universe was opaque, a roiling fog of plasma where light couldn't travel more than a short distance before being absorbed or scattered. But 380,000 years after the beginning, the temperature dropped below 3,000 degrees Celsius. Suddenly electrons could bind to protons to form neutral hydrogen atoms. Light was freed, the fog cleared, and the glow from that moment has been traveling through space ever since, stretched and cooled by the universe's expansion into microwaves, a faint whisper of the hot, dense beginning. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were trying to eliminate mysterious noise from their antenna. No matter what they did, no matter where they pointed their telescope, they detected a persistent background hum. They even cleaned pigeon droppings from the antenna, thinking that might be the source. But the noise remained. What they had found, unknowingly, was the cosmic microwave background, the echo of the Big Bang itself. They had heard the universe's first light, now ancient beyond measure, filling all of space with its ghostly radiation. We've mapped the cosmic microwave background with exquisite precision now, and it's not perfectly smooth. There are tiny temperature fluctuations, variations of only a few millionths of a degree. But those fluctuations are incredibly important. They're the seeds of everything. Regions that were slightly denser, 13.8 billion years ago, had slightly stronger gravity, which pulled in more matter, which created even stronger gravity. Over hundreds of millions of years, those tiny ripples grew into galaxies, clusters, and the cosmic web we see today. Every galaxy, every star, every world, including Earth, including you, traces its existence back to quantum fluctuations in the fabric of the early universe. We are the descendants of randomness, patterns that emerged from chaos through the patient alchemy of gravity and time. Let's venture even closer to the beginning now. Before the cosmic microwave background, before atoms could form, the universe was smaller, denser, hotter. Rewind time far enough, and the entire observable universe, all 93 billion light-years of it, was compressed into a space smaller than an atom. At the very beginning, in the first tiny fractions of a second, the universe underwent something called cosmic inflation. In an impossibly brief moment, lasting perhaps 10 to the power of -32 seconds, the universe expanded exponentially, doubling in size over and over again at a rate faster than light. In that instant, a region smaller than a subatomic particle inflated to the size of a grapefruit or larger. Inflation explains why the universe is so uniform, why distant regions that should never have been in contact look so similar. They were in contact incredibly briefly before inflation tore them apart. And before inflation, before that first fraction of a second, we don't know, our physics breaks down, general relativity predicts a singularity, a point of infinite density where time itself begins. But we don't have a theory of quantum gravity. We can't describe what happens when both quantum mechanics and general relativity become important simultaneously. The very first moment, the Planck time, 10 to the power of -43 seconds after the beginning, remains beyond our understanding. It's a boundary of knowledge, a place where our equations dissolve into uncertainty. Perhaps time itself emerged with the universe. Perhaps there was no before, because time didn't exist until that first moment. The question, what happened before the Big Bang, might be like asking, what lies north of the North Pole? A question that seems meaningful but ultimately isn't, because the framework within which it's asked breaks down. Time, space, matter, energy, all of it might have emerged together, a package deal, existence itself springing from what? We don't know. Quantum foam? A fluctuation in a field we haven't discovered? Another universe collapsing and rebirthing? The multiverse spawning endless bubble universes? These are speculations, dreams, mathematical possibilities. The truth remains hidden in that first, immeasurable instant. And yet here we are. Somehow, from that impossibly hot, dense beginning, the universe expanded and cooled. Particles formed, forces separated, atoms assembled, Stars ignited, galaxies gathered, planets coalesced, chemistry became complex, life emerged, consciousness awakened. And now, 13.8 billion years later, a pattern of atoms that calls itself you floats in imagination at the edge of time, contemplating the origin of everything, asking the ancient questions. Where did we come from? How did this all begin? Why is there something rather than nothing?
These are the deepest mysteries, and they remain mysteries still. But the wonder of it, the sheer improbability and magnificence of existence that we can grasp. We can feel it here, surrounded by the ancient light of the cosmic microwave background, standing at the shore of time itself.
Rest now. Let your mind settle. We've traveled from Earth to the edge of the observable universe, from the present moment back to the first whispers of creation. You've seen planets and stars, galaxies and galaxy clusters, the cosmic web, and the echo of the Big Bang. You've journeyed farther than any human body could ever travel, witnessed timescales longer than any human life could ever span. And yet in a way you've never left home, because all of this, all of space, all of time, every atom and every photon exists within the same universe that contains you. You're not looking at something separate, something out there. You're looking at yourself, at your origins, at the vast and ancient process that created you. The universe made stars, and the stars made atoms, and the atoms made worlds, and the worlds made life, and life made consciousness, and consciousness made wonder. And wonder brought you here, to this moment, this quiet contemplation of everything that is. Thank you for traveling with me. There are still more wonders to explore, more questions to ponder, but for now, simply rest. Float in the gentle darkness between moments. Know that you are home. Know that you are loved by the cosmos that made you. Know that your existence, however brief, is part of the greatest story ever told, the story of the universe coming to know itself. We'll continue soon. For now, peace. And with that, thank you, listener, for getting to the end of this video. I hope you enjoyed and found it relaxing. There will be other videos uploaded often with fascinating topics. Please like and subscribe to this channel. Your support is appreciated.